Okay, it's 3 o'clock. I think we can start now our afternoon session. We have 3 talks, and the first talk of the afternoon session will be given by Professor Tsvi PIRAN. Professor PIRAN, are you here?
Yes, I'm here. Just a second.
Okay.
You might,
Please share your screen and let's check if it works.
one second. Yeah, do you see the?
Not yet.
Yes, we are here. Good afternoon.
Good afternoon. Do you see me?
Yes, I see you.
Okay. Now we
Okay,
see you.
and now I'll share the screen.
Tsvi, we have gone.
Share screen. Okay, share.
Okay, now we see your screen.
You see my screen?
Yes.
You still see it?
Yes, there is a small window, build order, so maybe you can put it away. There is a small window on the right part of your screen.
I'm not aware of that. Does it move forward?
Yes, it is moving, but there is some small window on it. Maybe you can.
I don't know what's the problem.
The one on the right.
No. Okay, play. I don't have something like this here. So,
Okay.
full screen window. Okay, it probably will work now. Share screen. How is that? Share screen. Do you still see my screen or not?
Yes.
Now it's stuck, I guess.
Stop sharing.
Okay.
Okay. Share screen.
Okay, now we see it full screen.
Now you see it, right?
Yes. So
Okay,
you can go ahead. The stage is yours. You have 45 minutes, please.
Okay. Good afternoon. And what I would like to do is to talk about to review some basic features of gamma ray bursts. Basically, to give an idea and motivation, why do we have the theories that we do have, and why we all picture a gamma ray burst as something like my background, with a compact source and a jet coming out of it. And we are convinced that we don't know many things about GRBs, but this structure is almost certain. So this is the structure of what I was saying, some basic facts on GRBs and implications. Then implications of jet propagation in stars. We heard earlier about jet propagation from within a car. And then I'll talk about the division of different kinds of GRBs that we have, long and short. And the next 2 talks are, so all this work, the first topics will be just review of things which are well known and well established. And then I'll talk in the second part, mostly tomorrow, about TeV emission from 1901-14C and other GRBs, and on possible understanding GRBs using gravitational waves, but different aspects of the gravitational waves. Okay, so let's go almost 50 years ago.
Today you give 45 minutes, and tomorrow as well?
Yeah, I think this is what I'm scheduled, right?
Yes. Now we will need, Tsvi, some of your presence to our talk. Therefore, we will have to discuss when to locate our talk in order to make sure that both Nakar and you are present to our presentation, but we will discuss this later. Go on, please.
Okay. So the first talk that I want to, the first issue that I want to discuss is the compactness problem. And this problem is very old one. It's understood for a long time, but in the context of GRB, it is almost 50 years old. And it was raised by Mel Ruderman very early on in 1974, in what was the first review talk on GRB. And it was highly influential, as you will see. And the idea is that already then it was known that GRBs have a non-thermal high energy tail. It wasn't clear how high it was at that time, but it was clear that it is going above half an MeV. So this is a possibility of pair production. Now, this problem does not depend on the model. I want to stress. The issue here does not depend on the details of the model that you can build. It is just based on the observation of high energy non-thermal photons that I am arriving to you at large fluxes. And these high energy photons can do pair production. Gamma gamma goes to E plus E minus. And the condition for this is that the energy of the two photons should be larger, the product should be larger than 2 MEC squared. And usually in this context, the way this is happening is a very high energy photon, which are very few, is interacting with a low energy photon that are very many. So the problem is not for the low energy photons, but the problem is for the high energy photon. Because the high energy photons see many more low energy photons for which this product can be satisfied. And if it's satisfied, it interacts and creates a pair. And the cross-section is of the order of the Thomson cross-section. So it's a very simple calculation to calculate the optical depths once you know what is the observed flux. So you take sigma Thomson, more or less. This is the energy density of the photons at the source times the typical size of the source. This is the optical depth. Now, to get the energy density, you take the total energy and you divide it by h nu, the typical energy of a photon. This gives you the total number of photons. And you multiply it by f, which is the fraction of photons which are above the critical energy, so they can interact. And you, to get the density, you divide by 4 pi over 3 r cubed, but you multiply by r, so effectively you multiply by 4 pi r cubed. And the 4 pi doesn't matter so much. The parameters are not very critical. And E, if you just see a flux, you don't know, but E is related to the flux that you see as the observed flux time assumed distance squared, so time 4 pi. So if you assume a distance from the flux that you observe, you know what is E, and if you know what is E, you can calculate this factor. Now, it is generally known that if you have a fluctuation on a time delta t, you expect that the size of the emitting source will be less than c times delta t. And so you take this factor for a gamma ray burst and assume that it is a cosmological distance, and you get something like 10 to the 15, which is much larger than unity, which means that cosmological gamma ray bursts cannot produce in a simple way the very high energy flux, the very high energy non-thermal flux. It simply doesn't work. And this is regardless of the model. You can I didn't say anything here about what is producing the photons, how the photons are produced. I'm just talking about the fact that there is a flow of photons going in our directions, and at the same time, there is high energy photons and low energy photons, and the high energy and the low energy photons may interact with each other and produce pairs. Once they produce pairs, the source will be thermal, and the source is non-thermal. Now, this led to the conclusion that GRB cannot be cosmological, as the total energy will be too large and compactness will be violated. This was one of the important conclusions of Ruderman paper, and I raised it because it is wrong. We all know today that it is wrong. But I show here is some figure of very old history of gamma ray bursts, the early history of the gamma ray bursts, the first 30 years. The first 30 years were dominated by this issue. Villa discovered gamma ray bursts in '67. It was announced only 6 years later in '73. Then Ruderman came with the compactness argument in '74. And then everybody concluded that GRBs are galactic. So until 1992, when Tsvi showed that the bursts are isotropic and they are not in the galactic plane. If they're galactic, we would expect them to be in the galactic plane, like all galactic objects, but they are isotropic all over the sky. So until then, 99.9% of the models, and there were many models, were all galactic. And all the community was working about flares on neutron stars. There was a whole industry. And then came Tsvi, but because there was so much work invested in this, and so much effort invested in this, and the belief was so well engraved into everybody's mind, then there was a big debate. People debated for about 5 years whether GRBs are cosmological or not, and there were huge discussions. Even so, there was, in my mind, there was no point to discuss it. It was clear immediately in '92. And some very well-known physicist, I won't mention his name, it doesn't matter now, but you all know the name, said in a public interview that if GRBs are cosmological, we need new physics. And I completely agree with him. The new physics, we need new physics, but the new physics was discovered in 1905. It's the special theory of relativity. And this was pointed actually the first, as far as I know, by Krolik and Pierre in, I think in '93, how to bypass the compactness by relativistic motion. And I'll discuss it in 1 minute. Then came Beppo-Sachs in '97, the observation of afterglow, and cleared the discussion. Even so, I think that the discovery that GRBs are cosmological is from '92, not from '97. This was supporting evidence. And from now on, we are all working on cosmological sources, cosmological models. So how, but the critical issue is the theoretical understanding that we can bypass the compactness problem. How do we bypass it? I'll come to this later, how to bypass it, to this slide later. It was out of place. So there are two factors that help you if the source is moving relativistic. The source, I don't mean here the whole system, just the emitting part, the part that produces the photons must be moving relativistically. The first time is now, instead of R equals C times delta T, we have C times delta T gamma squared. Gamma is the Lorentz factor of the emitting region. So we see here a factor of gamma squared, which increases R significantly. And if you remember, R is here in the denominator. So if we increase it by a factor of gamma squared, this will decrease and will help to make this number smaller. And the second factor is that the observed photons are gamma times have the energy at the source. The observed energy is larger by a factor of gamma than the energy in the source. So if I see a photon of half an MeV, at the source it does not have half an MeV. It will have less energy, and if it has less energy, it cannot produce pairs. So the number of effective photons that are relevant to producing pairs decreases because of this shift of the blue shift of the observed frequency. So if I see a given photon at the source will have lower energy and it will be less prone for producing pairs. So this factor of R, which is proportional to gamma squared, since we had R squared here in the denominator, this gives me gamma to the -4. This factor that we have less photons tells me that the fraction of relevant photons is proportional to the fraction of observed photons times gamma to the -beta, where beta is the slope of the density of the spectral slope of the number of photons. And together I get here factor of -4 minus beta. Beta is of order 2 in the observed gamma reburst, so I have here gamma to the 6. And this means that if gamma is about 100, I can fix the 10 to the 15 because 100 to, or slightly more than 100, 300 or something like this will fix this 10 to the 15, and I get rid of the compactness problem. So this is how relativistic motion of the source solves the problem. And I don't know, and I haven't heard of any other way of fixing this problem. Again, this does not depend on the model that you are building. This just depends on the observations, on the taking the observed spectrum and transferring from the observed spectrum, learning what are the conditions that are happening at the source. So this is why this is critical, and this is why GRB models are based on relativistic outflow. Now, the simplest version of the compactness problem is that gamma goes to E plus E minus, and I take the high energy photon, a photon from here, and I ask how many photons are there and try to calculate them. But there is a second variation of the compactness problem. This was pointed out by Sari and Litwick in 2001. And the second version of the compactness problem is the following. The total number of pairs created by high energy photons and low energy photons cannot be too large. If the total number of pairs is too large, then we have too many electrons. And if we have too many electrons, the optical depths for these too many electrons will be too large, and we will not be able to have a non-thermal spectrum. Sometimes this criteria is more critical than the previous criteria. It is slightly more difficult to calculate. I will not go here over the whole equations. This part of these formulations are taken from a paper by Tatsuya Matsumoto and Ehud Nakar and myself. And this shows example, this is an example here of 1708-17 that shows that even in this case, which was a very strange burst, the minimal Lorentz factor was about, of the emitting region, was about 4 or 5. Not 5,000, not a few hundreds, but still significant. So this is the compactness problem. And again, the take-home message is that the emitting region, not the region where the energy is produced, but the emitting region, the region where the photons are produced, must be moving relativistically towards the observer. This is a fundamental building block of the model. A second part This is, I mentioned, was the second compactness, and this is when it applied to 1708-17. Okay. Now, let's take a particularly strong burst, 1304-27A, one of the strongest bursts observed. The total energy observed on Earth, the total flux of energy, was 2 × 10⁻³ ergs per centimeter squared. The distance was equal 0.34. And now this means that the total isotropic energy, which was emitted, now I realized I made a small mistake here. It's not 3 × 10⁵, it's more than 10⁵. There is a factor of 4 missing in my calculation. So it's about 10⁵ ergs, which means that the total energy seen in gamma rays is comparable to the rest mass energy of a sun. This is a lot of energy. It has 2 implications. This is extreme, but in other bursts, energy is also between 10⁵ to 10⁵. Only formation of compact object can produce so much energy in such a short time. Again, I say only, you may come with a different idea, but I don't know of any model today which does not involve production of a compact object, formation of a compact object, in order to produce this much energy. For example, in a regular supernova, we get 10⁵, 10⁵2 ergs, something like this, depending on how much, if the supernova is strong or not. We get 10⁵3 ergs in neutrinos, but they escape and we don't see them. But this suggests that the source must involve formation of a newborn compact object, either a neutron star or a black hole. The second, so the emission must involve formation of compact object. This is a take-home lesson, but at the same time, the emission cannot come from the vicinity of the compact object. Why the emission cannot come from the vicinity of the compact object? Because if I try to put here something like RG, like the vicinity of the compact object, I will get something not 10⁵ here, I'll get more than 10⁻²⁰. I'll get huge compactness if I try to get the energy directly from the center. So things are more complicated. So this is the second take-home message, and this is beginning to be slightly model dependent, but again, I don't know here any way to avoid formation of compact object if you want to get so much energy at a short time. The second thing is that this guy, again, I correct an error here. It should not be 3 × 10⁵, it should be 10⁵. If I have here 10⁵, this is the rest mass energy of a whole star. But this is just in gamma rays. It is inconceivable to think of a model. Again, this is now beginning to be slightly model dependent, but it is very difficult to imagine a model in which the efficiency of converting the available energy to gamma rays is 1. It's difficult to imagine such a high efficiency. And we know that it cannot be 1 because it's not only gamma rays. We have also the afterglow, we have some other things which are coming out. We must leave energy for that. Actually, in many people argue that the energy of the afterglow is larger by a factor of 10 than the energy of the observed gamma rays. So this means that epsilon gamma will be 0, at most 0.1. But whatever the value is, it cannot be 1. And 10 to the 54 is very uncomfortable because of the large involved mass and the required efficiency. So the conclusion from this is that this is isotropic equivalent energy, but this is not the true energy because there is beaming. And if there is beaming, then I have to multiply this number by about a factor of the beaming factor. With this will reduce it. And a typical reduction that people are talking about is somewhere between 1/20 to 1/50. And this brings the energy to something reasonable and the efficiency to something reasonable. So this is the next take-home message. The emission region must be jetted. We have independent evidence for jets, which is somewhat model dependent, this is the evidence is actually model dependent, not somewhat model dependent. One evidence is from what we call the jet break. It was predicted that the afterglow, if the afterglow is coming from a jet, it will have two phases, initial phase, and then at this region, the Lorentz factor goes down to 1/θ, 1 over the opening angle of the jet, and then it curves down and goes down steeper. This was a prediction. Which was done in 97, 98, before this jet was observed. And this is the first observation of a clear jet break, what we call a jet break. And it is seen since then in many, many other events. Another example of this, which is even nicer, this is in the optical, in the V and R band. But if you look at the radio, it is even more dramatic. The dotted line here is what you expect from a spherical afterglow. The solid line is what you expect from a jet. And this is what was observed. These are the observations. So again, this was, the prediction was made before the observations, and by now we have many other events. As far as relativistic motion, by the way, we have at least one case in which we saw direct evidence for relativistic motion in the afterglow phase, not in the Tromp phase, by motion of the centroid of the afterglow. So even so, these arguments are very basic, and I cannot see how to avoid them. There are supporting evidence. For example, another supporting evidence for the rate of for jets appears in short gamma ray bursts. In short gamma ray bursts, is believed that they are accompanied by merging. They are resulting from merging neutron stars. Then to reconcile the rate of expected rate of observed emerging neutron stars with observed rate of short GRBs, we must come with a beaming factor of about 50, which is just about right to reconcile this, but it was also derived independently from GRB observations. So let me put all this together. GRBs are produced during the formation of compact objects and involve relativistic motion. And one more way to put it, the energy must be generated near the compact object. So we have one phase of an engine which is generating the energy. Then the energy must be transported relativistically to a large region. This is the transport phase, which the relativistic jet is taking the energy which was generated here at the engine and sending it out to large distance. At large distance, then this energy is released. It's converted to the observed photon, and we see the emission. Typical scales are, this is something like 10 to the 6 centimeters. This transport here goes from 10 to the 6 to 10 to the 13 to 10 to the 14, depending on different models, what different model wants, the details of the different models. And then there is a conversion and emission of this energy to photons at something like 10 to the 14 to 10 to the 15 centimeters. This large conversion region is needed in order to enable the high energy photon to escape. Anything with very high energy, which is produced deeper, will be absorbed. And once it is absorbed by Perk reaction, it will create mass because these additional pairs will make the whole spectrum thermal. So, yeah, I think that I can make a short break here for questions up to here. If there are any questions, I will continue with the implication of this, but are the questions up to here?
Can I ask a question?
Sure.
Yes,
yeah.
Very nice talk, by the way, so far. Is there any idea, do you have any idea what the compact source object would be?
In principle, it is most likely, I think that in many cases, especially in long GRBs, it is a black hole, but it could also be a neutron star. And here begins the whole big difference between different people. I mean, some people will believe that it is a neutron star and the compact source is a magnetar, and the energy source is the rotational energy, which is transferred by the magnetic field and so on. So there is a big, here we begin to have debates, but the fact that it's a compact source simply comes from energetics, because you need to release the binding energy of a compact source to produce so much energy in such a short time.
Sure. Thank you. Thank you very much.
Yes, I enjoyed this part of the talk, like as usual. But I would like to caution Tsvi about a point. We agree practically on every point you have made. And we agree also, but we will try to show that tomorrow, that the energy comes exactly at the moment of formation of the black hole, which is practically immediate in our model, in which you have accretion from the supernova into the companion neutron star. The companion neutron star becomes supercritical and form a black hole. And that is the region in which we have what we call a the UPE phase, the ultra-energetic prompt emission phase. You will hear this tomorrow, the UPE phase. And indeed, that UPE phase has gamma factor exactly of the order of 100 in order to reach transparency. Therefore, on this we fully agree. The part we do not agree is that we are speaking not of a single event, but due to the self-similarity, we are speaking about a series of events. This is where the difference is. The difference events much shorter, which they obtain the transparency globally in all this UPE phase. And this is a conceptual difference. But all the quantity that you are mentioning are correct. Namely, correct that it comes from a black hole, correct that the gamma factor is 100, correct, that you need that, and so forth and so on, but you have not one process, but a series of events, very short in the reference frame of the source and repetitive. This is the key idea that we are pursuing, and we will be happy very much to discuss.
Yes, but I want to point out here that so far I didn't assume how the energy is produced. It can be produced by series of events. What I care is that at a given moment of time, I have these two photons are arriving. One is very high energy and one is very low energy. And this is what my detector sees. I don't care if it was produced by two successive events which were separated by some short time or not. But my detector sees the two photons arriving at the same time. If the two photons are arriving of more or less the same time, they were at the same time in the vicinity of the source. And if they were at the same time at the vicinity of the source, they would have interacted and produced pairs. Therefore, the origin of these pairs cannot be very near the black hole. This is what you are saying does not change the argument here, because this photon and this photon were moving together, and because I saw them together, and since we assume that they are all moving with the speed of light, they were at the source at the same time. And if they were at the source at the same time, we will have this problem.
Well, we will discuss.
Okay.
But I want just to point out the key difference.
Yeah, I see the difference, but I'm not. I did not even discuss what is our model, what is the
Yes.
standard model. All that I'm saying is that the models have three parts: energy generation, not photon generation at the source, transport of the energy to large distance, and conversion of the energy from whatever form it was coming out. Could have been formed by magnetic form or by kinetic energy of the photon, of the kinetic energy of the matter, or whatever. These are the two classical ways. You transport the energy, and then here you dissipate the energy and produce the photons. You cannot produce the photons here, because if you produce them, they would immediately produce pair annihilate with the very strong background soft photon field. So any high energy photon produced near the source is dead, and it is not only dead, it makes trouble for everybody else, because the accompanying pair will make a whole mess and will produce a thermal spectrum.
Well, anyway, we are going to, instead, we need to make a model, and we do make a model in order to fulfill our condition. It cannot be done without entering into the issue of how the energy is produced from the black hole, microscopically. This is our difference. Okay?
I intentionally did not try to produce a whole model.
Yes, but
I was just going to give a general review of what is the basic concept.
Okay, but in our case, we intentionally look how this can be done from the physics of the black hole.
Yes, I understand. Yeah, but it must be, whatever is done must be taken care of this, satisfy this constraint.
Absolutely, absolutely.
Okay, so what I said so far is, in my mind, largely model independent and can be applied for any or most GRB models. And well, I'm thinking that I ran out of time, so it's already 40 minutes. So maybe it's not a good moment to start a new topic, because the next topic that I wanted to discuss is about jet propagation in the star. This is related to what Udi Nakar said, but what I wanted to discuss is the implication of this. But maybe it's not a good time to start this new topic. So I suggest to stop here and then continue tomorrow after or before this talk. This you have seen, the jet propagation.
If I may ask another question again at this
Yes.
point. It's Gregory. Okay, I'm really very nice general presentation. I want to ask you really on this point that you touched, the process of energy conversion, efficiency, and also a question related to beaming somehow. But let's go one by one. This model, I mean, not what model, exactly this point you show, there is a necessity of energy generation near a compact source, so evidently gravitational energy is involved, right? After that, there must be this transport, which, if we are lucky enough, just one mechanism is involved, but probably not only one. I'm talking specifically, let's take thermal acceleration of the fireball, or take magnetic models with magnetic acceleration. So energy conversion from gravitational energy to magnetic or thermal energy, then acceleration process itself, then dissipation of this energy, and then eventually radiation, either direct or indirect. So all this involves multiple stages, and as you pointed out, each conversion process of energy requires efficiency, not 100%. So after, at the end of the day, we probably end up with extremely low efficiency. I mean, all the models, not only your favorite one, because of many stages of energy conversion. This partially, okay, if we got there, just one addition. This partially can be overcome probably with the beaming phenomenon, because the more energy you need in the source, the highest beaming factor you put in. But at the end, maybe this also fails because of multiple efficiency problems you encounter. What do you think about it? Thank you.
The efficiency is not so bad if you talk about something between 10 to the 50 to 10 to the 52 ergs. In this case, the effective epsilon gamma, what we call what I wrote as epsilon gamma, is this is comparison of the observed gamma ray energy to the observed total energy involved is of order 10 to the minus 2, 10 to the minus 3, which is a small number, but sufficient. Because, for example, if we have 10 solar masses and the efficiency is 10 to the minus 3, then we get 10 to the 52, then to the 52 ergs. So this is not terrible. If you have 10 solar masses and you want to get 10 to the 54, then you need efficiency of 0.1, which is very problematic. So I don't see a big, of course, but the problem is the following, that what I try to portray here is a general overview of what a GRB model must include. And I intentionally did not try to be very specific. There is an engine that produces the energy from the collapse to formation of black hole, for producing somehow very quickly the needed energy, and then moving it out and then converting it. I agree that it is very difficult to produce here epsilon equal 1. This is why of order unity. This is why you need beaming.
Okay, thank you.
Okay, some other questions?
Not understand last word. What link being? Tsvi, I did not understand your last word.
I'm saying that
The last word.
I guess I agree completely with Gregory that efficiency is a problem, and because of this, we need beaming. We cannot produce 10 to the 54 hertz burst because of efficiency problem.
Yes.
Yeah. Okay, so thank you, and I will talk tomorrow morning if I understand correctly,
Yes,
right?
yes, you have the second talk tomorrow.
Okay.
So let's thank
Thank you
again
again.
Professor Piran.
Thank you.
Beautiful talk.
Okay.
Okay,
Bye-bye.
the next talk is by Nick Mavromatis. So Professor Mavromatis, you can try to switch on your slides.
Yes, it says that now I can.
Yes, we see your
You see,
slides.
so let me go. Sorry, let me go full screen. Is that right now?
Okay, there, right? So the stage is yours, so go ahead.
Thank you. So my talk will be, although it will be different from what we have heard this morning and in the previous talks, which I enjoyed very much, all of the talks. Nonetheless, the gamma ray bursts, as it was mentioned, can be used for understanding cosmology and dark energy issues in our universe. So what I'm going to discuss is, first of all, a cosmology which is not like the conventional ones, but is characterized by the so-called gravitational anomalies and the presence of axions, i.e. pseudoscalar fields. And this, I will argue, they will lead to modified profiles of gravitational waves, but also to some interesting dark matter properties, especially warm dark matter in galaxies. And I will connect these two issues. So let me outline the talk. First of all, I will motivate it. Then I will discuss the model, which is inspired from string theory. It's not microscopic string theory, but it is inspired from string theory, and it contains both torsion and gravitational anomalies, and the actions are related to the totally antisymmetric part of the torsion, plus some other actions in string theory arising from compactification. Then I will discuss how primordial gravitational waves can induce condensates of such gravitational anomalies. And here is where the interesting part comes. Anomalies, when condensed, can lead to some Lorentz sensitivity violation by axion backgrounds. This is an innocuous sensitivity violation, which is similar to what happens, for instance, in electromagnetism, if you have an electric field along a fixed electric field along a given direction. Lorentz symmetry is broken, and then in this particular case, PT is also broken. This violation will lead to a new kind of inflation of the so-called running vacuum model type, which does not involve external influence. But then it induces a very important property, in my opinion, that such a model could lead unavoidably to enhance cosmic perturbations and the densities of primordial black holes, which in this case can play the role of dark matter components together with other components, the axions that are induced by torsion. My point of view here is that the dark matter doesn't necessarily have to be characterized by a dominant species. It may be more than one depending on the cosmological era. The post-inflationary eras are characterized by these Lorentz sensitivity violating action backgrounds that remain undiluted until the end of inflation. And then they lead to an important property, namely matter-antimatter asymmetry by means of baryogenesis through leptogenesis. Here, there is a very important role of right-handed sterile neutrinos that the model includes. I will come to the modern inner phenomenology eventually, where deviations from the lambda CDM as a result of this model will occur, and they can lead to alleviation of the cosmological data tension, the Hubble tension, or the growth of data tension, of cosmological structures tension, if these tensions are not due to statistics. Finally, but not less important, I will discuss warm dark matter in galaxies, and here is a work that I have done with Carlos Arguelles, Jorge Rueda, and Remo Ruffini, and is based on the fact that the right-handed sterile neutrinos that I talked about may play a role in the galactic structure if one uses the modified galaxy profile due to Ruffini, Arguelles, and Rueda, the so-called RAR profiles. And then I will summarize. So the motivation is standard. I won't spend time on it. I'm trying to understand the dark matter of the universe. The lambda CDM is okay from large scales, but is not an answer, is not a model. There is no microscopic explanation. So we will try to understand what is the nature of dark energy, dark matter. We haven't seen primordial gravitational waves yet, but I will argue in this talk that they may play an important role. And also I will try to see, as I mentioned, whether inflation is due to fundamental inflatons or some non-linearities of gravity, and I will argue in favor of the second, and in analogy with Starobinsky, but slightly different. As I have already mentioned, dark matter can depend on the era and may be characterized by more than one species. And I will discuss in this talk the role of warm sterile neutrinos, dark matter in the galaxies, but also axions. As I mentioned before, another motivation for my talk is the potential elevation of 8.0 and sigma 8 galaxy growth data measured today. But also, since I mentioned about unconventional leptogenesis, I will try to present the geometric way for a macroscopic understanding of matter and antimatter asymmetry due to torsion. In fact, in the conventional case, such matter and antimatter asymmetry is explained through CP violation. However, this has its drawbacks, of course, but in this particular, and I will not go through the models, the conventional models, which are CPT conserving, but I will try to present a model in which an induced CPT violation due to the aforementioned Lorentz symmetry violation by means of action backgrounds in the early universe can induce this matter and antimatter asymmetry. So in particular, I will argue that deviations from lambda CDM and elevation of cosmological data tension in the current era, plus the observed matter and antimatter asymmetry, can be linked with these microscopic string theory inspired models with anomalies and induced condensates of gravitational anomalies through primordial gravitational waves, which can lead to Lorentz and CPT violation, and also with the geometric torsion interpretation of action dark matter and enhanced gravitational perturbations through primordial black hole modified densities. The important point of the matter and the matter in the matter and the matter asymmetry, it will be an important role will be played by right-handed sterile neutrinos and axions, and as we shall see, also these particles can play an important role in galactic structure. Now, the ingredients that I will use in the talk is the gravitational anomaly condensate. This is the dual of the Riemann curvature tensor. I will explain what this means. The stringy action fields, I will use two types of fields. One is the so-called string model independent action, which I will explain where it comes from, and the other comes from compactification. For the models, for the toy models I'm going to discuss, I will use only these two kind of actions, but you may have many actions which can be constrained further by observations, as I will discuss at the end. Here we'll only restrict ourselves to two actions. And then the important point is the action coupling to the anomaly. The actions themselves will lead through background, especially through this action, or which violates spontaneously and CPT symmetry. And this can lead to leptogenesis in the presence of sterile neutrinos. On the other hand, this coupling of actions to anomaly will lead to a running vacuum model, or the so-called RVM model of inflation without external inflaton fields. So let me describe the model and the role of gravitational anomalies and torsion. The model comes from string theory, the massless or the ground state of superstrings. The massless multiplet of bosonic strings of the ground state of superstrings consists of the delaton, which is a spin 0 scalar, the graviton, which is a massless spin 2 traceless symmetric tensor, and a spin 1 antisymmetric rank 2 tensor. In general, these are live in higher dimensions, but they could survive in 4 dimensions. And this is what I'm going to assume. I will concentrate on this Karl-Bramon and the symmetric tensor, which is like a gauge field. It's characterized, the closed string sector that I'm going to discuss and restrict myself onto is characterized by a U1 symmetry, which means that the effective action to lowest ordering derivatives is given by gravity plus the kinetic terms of the dilaton plus these terms where an exponential of the dilaton couples to this field strength. This is the curve of this gauge field with two indices. The dilaton I will assume constant throughout, stabilized somehow by its potential. The important point to notice, which will lead me to the coupling of the actions to anomalies, is the fact that anomaly cancellation in string theory requires the modification of this field strength from the kernel of B to this These are the so-called Chern-Simons term. This is a spin connection in 10 dimensions. These are gauge fields in 10 dimensions. This is the Green-Schwarz mechanism, and the required anomaly cancellation could occur in the extra dimensions. I will not cancel the gravitational anomalies in 4 dimensions. This generalized field strength, assuming a dilaton, a constant dilaton throughout, can play the role of torsion in the sense that it can be absorbed in a generalized curvature scheme. And actually, this absorption holds also in alpha prime quartic and derivative terms. And the generalized connection is not symmetric because this is totally antisymmetric in its indices, and that plays the role of torsion. Now, actions, how these actions are related to torsion. Before going to that, first of all, let me stress that in string theory, you do not have any cosmological constant because the scattering matrix will not be defined in perturbative strings in the de Sitter space where you have an horizon, and therefore you cannot define the in and out states. You will only generate the dark energy dynamically, and it will be time dependent for consistency. We shall see that. Now, the action, how is it related to the antisymmetric part of distortion? First of all, notice that there is an identity. If I act with the exterior derivative on the dual of this form, this involves the epsilon mu rho sigma in 4 dimensions, I get this anomaly term. Now, notice that my action is quadratic to this order, therefore in a path integral, I can integrate over dh. And once you implement in this path integral, this Bianchi identity as the delta function constraint, this delta function constraint is implemented by a pseudo-scalar Lagrange multiplier term because the delta function is CP invariant, and therefore this term is CP violating, and therefore you need to multiply it by a pseudo-scalar CP violating term to make it CP invariant. And that is the result, including the fermions. The fermions also couple linearly to the H because the H is the torsion and it appears in the covariant derivative. That's the important point. So you see, by having this modified, if you like, field strength of the action, you generate a field strength action of the antisymmetric tension, you generated an anomalous CP violating coupling between the action field, which is a Lagrange multiplier, and after integrating out the H field becomes dynamical, and here we have the fermions. Notice that the action couples in a derivative way with the fermions. And these are the dual fields. The F nu dual you're all familiar with. The 0I dual is the magnetic field, which is dual to the electric field, and an analogous dual relation characterizes the Riemann curvature. Notice that classically, the derivative of the action field is proportional to the dual with respect of the tension. This is the Levi-Civita covariant tension. This term for Friedman, Robertson, Walker, this F term vanishes. And this field, this Lagrange multiplier can be called gravitational action or string model independent action because it exists in all string theories in the way explained. So this is our model, consists of fermions and bosons, and the important point is the anomalous terms here. These are gauge fields, which eventually in the model, however, that I will discuss later on, I can set them to 0 and I will explain why. At the moment, let me explain that this string model independent action, this coefficient in front of the B defines the action coupling constant as usual, because that's the coefficient of the term which couples the action to the anomalies. And from compactification of strings, you don't have only this string model independent action, which exists in every string theory, but also you have actions that depend on the details of compactification, and after canonical normalization, they also couple to the anomaly terms, but with their own coupling constant, which are different from the coupling constant of this string model independent action. So the anomaly terms play an important role. First of all, by partially integrating the fermionic coupling to the anomaly, you see why this is also an anomaly, because the gradient of the chiral scalar, if you have a chiral fermion, the gradient of the axial current is also proportional to the anomaly term. So these terms are similar, and in fact, one can cancel the other, as we shall discuss at the end of the inflationary period. Now, let me pass on to discussing the properties of this anomalous theory. First of all, if you have a gauge field anomaly, a chiral gauge anomaly coupled to an action, this is topological and it does not contribute to the stress tension because its variation with respect to the metric tension vanishes. This is not the case, though, if you have this gravitational anomaly, which seems to spoil conservation of the stress tensor. So people might worry about the diffeomorphism invariance in quantum theory. This is because the variation with respect to the metric field of this gravitational anomaly term gives rise to the Cotton tensor, which is defined as the dual of the Riemann tensor, the covariant derivative of the dual of the Riemann tensor, and is proportional, of course, to the derivative of the action. Why? Because if the action is constant, these terms, the anomaly terms, are total derivatives in 4 dimensions, and therefore they don't play any role. And that is captured by the fact here that all these terms are proportional to the derivatives of the action. The Cotton tensor is also traceless. An important property is that because it's a higher derivative term, it contributes not necessarily positive contributions to the vacuum energy, which will play a role later on. This is like the Gauss-Bonnet term in 4 dimensions, which is also quartic in curvature, but because in our theory we have considered the dilaton as being constant, the Gauss-Bonnet is the total derivative in 4 dimensions and plays no role. Now, what I mentioned about the matter conservation, if you have Einstein's equation in the presence of this Cotton tensor, and that's the matter tensor, you will see that because the Cotton tensor is not conserved, but is proportional to the anomaly, the matter tensor appears not to be conserved. So you would worry about the diffeomorphism invariance breaking by gravitational anomalies. However, this is not so, because you can always define this improved tensor by absorbing the Cotton tensor into this definition of the improved stress tensor. And essentially, there is no problem with the diffeomorphism invariance because it simply describes an exchange of energy between the axions and the gravitational anomaly set. And this is an important point, which if you have, for instance, a rotating black hole, a curved black hole, the action sources that black hole and vice versa. Let me now go to describe briefly the origin of primordial gravitational waves and how anomaly condensates can arise in this theory before discussing the phenomenology. First of all, in this model with Joan Sola and Spiros Vasilakos, we have proposed that the model in our early universe is not characterized by any gauge field or chiral matter or matter in general, except for the bosonic fields that that exist in the massless gravitational multiplet of strings, or the ground state of superstrings, which is the graviton and the symmetric tensor and dilaton. And since the dilaton is set constant, it's stabilized somehow by its potential. In our early universe, we are only having the actions, the gravitational action, and the graviton itself. This total, here, the second line expresses the fact that the anomaly terms are expressed as a total current, and we perform a partial integration here, assuming that in the early universe, the boundary terms vanish. If, therefore, you don't have gravitational waves or any other chiral perturbation which will source this RR tilde term, like a primordial rotating black hole or anything else, you need a chirality to have this term non-zero, then the matter, the gravitational action, would be completely massless, and a massless matter without potential, there's no potential of this action, as we have seen, will constitute a stiff matter. This is like Zeldovich model, but Zeldovich predicted the pre-inflationary era of stiff matter in the beginning of the universe, but consisting of baryons. Here are just bosons, axions. Now, primordial gravitational waves, what is their origin? Their origin, and I will be very brief here, could be multiple. It could be due to primordial black holes, but also one scenario, which I'm exploring here, consistent with this assumption that only gravitational degrees of freedom play a role in the early universe, could be the role of dynamical breaking of supersymmetry. I'm not discussing, of course, details here because that would take me out of the scope of this talk, but I mentioned that if you have a dynamical breaking of supersymmetry, which can occur, let's say, through a condensate of the partner of the graviton, hence I'm still staying within the gravitational multiplet of the string in agreement with the spirit of our model, then you may have a statistical bias between the two domain walls that are characterizing the double well potential of this dynamical breaking of the gravitino through some percolation effects. And then the system is flowing into this vacuum. There are imaginary parts here. You can, so the system is unstable, it will flow there, and then it will be stabilized by the running vacuum in model inflation, which is induced by gravitational wave condensates, as I will argue now. However, there is the top of the potential here, which dynamical breaks supersymmetry, and you see that the bottom of V here is positive. This is the sitter. because the Sitter space is not compatible with supergravity. You have a first hilltop inflation, which is not necessarily slowly rolling, but which defines an early inflationary era, which is interpolated by a stiff matter, and then the RVM inflation that I'm going to discuss now, which is induced by anomalies. So this is the cosmology we discussed, and the first hilltop inflation ensures that any inhomogeneity that exists in the universe are washed out before the universe enters in the RVMGW induced inflation. Now, let me discuss now this phase and how Lorentz sensitivity violation arises and how inflation arises without external influence. I'll just discuss that this time is non-trivial if you have gravitational wave present or any other chirality. In this particular case, I will argue now that a condensate of this term can lead to Lorentz violation spontaneously. First of all, how formally could be a condensate? A condensate means that I develop a VEV plus the quantum corrections. The VEV, if this is approximately constant, will induce a de Sitter cosmological type term with mild dependence through the age, through dependence of the Hubble parameters, as I will argue. Equivalently, because this term is a total derivative, you can partially integrate, assuming that in the boundary of the space-time, any contribution vanishes from gravitons and their derivatives, and you could write this term as the derivative of this type of condensate. What can we do to demonstrate inflation? First of all, let me assume inflation, compute the condensate by using the fact that this anomaly term is a total derivative, deduce a Riemann vacuum behavior, and then explaining how the Sitter arises dynamically, which means that our assumption is self-consistent. So let me assume that there is a proper number density of sources of gravitational waves. I may assume of order 1, but I can relax this assumption. I assume isotropy and homogeneity, so the axion field depends on time, and the anomaly equation, which was here, also depends only on time. The spatial components are subdominant. So that's the anomaly equation. You can compute in a way that I don't have time to explain, in the presence of primordial gravitational waves of non-zero chirality, in other words, left-right modes of the graviton modes. So this is a quantum gravity in a weak limit approximation, but you can compute the condensate, and you can cut off the ultraviolet divergences of the graviton modes by an ultraviolet cutoff mu, and that's the result. Theta is the proportional to the derivative of the time derivative of the action, and is assumed slow rolling, an assumption that I will self-consistently derive now. And h is the Hubble parameter, which may be also slowly rolling. So from the equation of motion of the action, you obtain this form, and you see what's happening. If there is, in general, if there is no condensate of anomalies, if there will be no anomalies, it will be box B equals 0. The anomalies, however, source a box B, and this admits this solution, B dot proportional to the time derivative of the anomaly. You can show by using the anomaly equations that actually the anomaly equation admits this solution. And notice what's happening here. Generically, the anomaly is washed out exponentially, like what you would expect in any inflationary theory. However, you may tune the parameters here, in particular the string scale, in such a way that the exponent is 0 and the anomaly is approximately constant during inflation. That means that you ensure constant anomaly if you assume that the ratio of the ultraviolet cutoff to the string scale is of order 10 to the 3. In this case, you get a constant anomaly and a constant B dot. And because B dot is proportional to the dual of the H field, that's what I was talking earlier, is a Lorentz and therefore CPT violating situation, because you have a vector field like a gauge field, that's the field strength of a gauge field, constant in space. So they are not, by the requirement of not having Transplanckian modes, you ensure that you have a B dot, which is almost constant, as we have just seen, can be parameterized in this way. The epsilon is a free parameter. If you want, this is not the field that drives inflation, but if you want to say that any slow roll inflation is associated with Planck data, you can assume this value, but not necessarily. So for us, it's a parameter. The slow roll condition, when combined with the absence of Transplanckian modes and the constant anomaly, can restrict the string scale if you assume that there are order 1 defects, order 1 sources per Hubble volume for the gravitational waves. But you may relax this constraint, and in fact, you can the string scale can be free, but then you can associate the string scale with the ultraviolet cutoff. That's an alternative way. It doesn't affect our conclusions. Let me now discuss inflation. What means inflation? From this relation means that I can solve this equation, which means that the time derivative of the action is constant and expanding in this way. An initial value plus this value. At the end of inflation would be, at the end of inflation, this would be n. And you will see that I can have, in general, I have a linear action dependence, but this term can be approximately constant if that term is much smaller than this term, which means that because if you require any voltage of order 55 to 60 or 70, you get this value. Now, you might worry that in string theory, people worry about distance Swammland conjecture, which I wouldn't like to enter. But if you have values of fields that are above Planck scale, you may induce an infinite tower of states, which could invalidate the effective field theory approach. This is not the case here because that's a total derivative. And essentially what you think is linear term is just the condensate of this, and the B dot is much less than M Planck. So the distance conjectures are unqualified. So estimating this inflation, you see that the vacuum energy, which consists of contributions from the axion, the anomaly term, the quantum fluctuations, and the condensate, acquire this form, is proportional to h squared and h to the fourth. That is actually what one calls a running vacuum model type, because in the running vacuum model type, you have an energy density that depends on even powers of the Hubble parameter, and in general time dependent through these parameters. In this particular case, you can prove an equation of state despite the time-dependent parameter of the age. The equation of state can be proven is actually not that is that of the true vacuum. The condensate, in fact, compensates for a phantom matter. If you consider only the quantum fluctuations of the anomaly and the axion term, you find the de Sitter type, but with a negative energy, but the condensate dominates, the condensate which is due to h to the fourth, and restores the positivity of the energy. So these are RVM terms that contain actually a scalar degree of freedom from the anomaly condensate, but no, it's not an inflaton. So this induce inflation. How? Well, that's what you have if you have the stress tensor in this case between matter, which is radiation, and whatever matter we have, the action in this particular case, and the vacuum, the RVM. That's the total value, and we have seen that this total value consists of that. Because the age is approximately constant, when you take the derivative, you end up with this form. Nu and alpha are defined by these coefficients here. This is a theoretical asserted is of order 1.17 to 1.37, so it's of order 1 here times 10 to the 7. And then you see that at early stages of the universe, this is the scale factor, there is a de Sitter, an unstable de Sitter space. Everything is unstable here, which is due to the h to the fourth that dominates. So here you get inflation. You cannot obtain this h to the fourth in conventional quantum field theories. You need the anomalies to do. And because the anomalies are CP violating, here you see another important role of CP violation for the early universe, unlike the traditional Zahav state. This is because of inducing inflation. One remark here, because the anomalies, as I mentioned earlier, contribute negative contributions to the stress energy tensor, you get this minus here, which is not dominant because the condensate is positive, but nevertheless distinguishes the model from conventional RVM, where this coefficient is positive. Actually, at post-inflationary cases, ordinary matter can still, or radiation can still lead to these sort of dependencies, but with positive coefficient. So this minus sign is a characteristic feature of the inflation. As I mentioned before, this undiluted axion background at the end of inflation is important, survives and can play a role for leptogenesis of the radiation era, as I will discuss briefly later on. Let me now go to these enhanced cosmic perturbations and density of primordial black holes. What we have discussed so far is an anomaly condensate, which leads to a linear action potential. And these are the scale. Such a potential could also arise in other appropriate brane compactification in superstrings. But in our case, it arises, you don't need a brane, it arises from this anomaly condensation. If you have another action arising from compactification, you could also have this. The action would also couple to that term with its coupling constant, and therefore you will have this term. Moreover, world-sheet instant or non-perturbative effects can lead to periodic modulation of this potential. The action potential, the B action or this compactification action could both acquire such terms. And because they are instant, they are suppressed by world-sheet instant or large actions. I mentioned that for an action of order 40, a world-sheet instant or an action of order 40, you may get very small masses from the quadratic terms here for the actions, which could still be compatible with ultraviolet dark matter. In brane compactifications, you may also get some linear terms in addition to the periodic modulations. So in general, you may have, during our inflation, this sort of potential, a linear B potential. I assume that this hierarchy that the worldsheet terms for the B action are negligible and only the compactification action are important. The incident effects of the compactification action are important, and therefore you have this potential, a linear B, a linear A, but periodic perturbation modulations of the potential with an amplitude that depends on A for the compactification action. I can distinguish these two cases here. One is the case in our model where the inflation is driven by the B action, which dominates and has this hierarchy of scales, and a model that exists in string theory in action monodromy where the inflation is driven by the compactification action, is a two-stage inflation, which is then prolonged by the B action. Both cases lead to an enhancement of cosmic perturbations, as I will discuss now. Let's start with this. You can plot, you can see the actions here because of the periodic modulations have this sort of stepwise, step-like features in the potential, and you see here the E foldings that would play the role of the inflaton, that would be the B field. And you see that in this potential, you can get the standard ratio of inflation, but a rather large ratio. That's a prediction of the model, if you like, a ratio tensor to scalar ratio, still compatible with the current limits. The spectrum, the power spectrum, actually the envelope of the power spectrum has surprisingly a logarithmic behavior as you can fit it. The red curve is the fit of this log and the black curve is our data. And this can lead to a resonant peak. If you have such a behavior of the envelope of the primordial spectrum of the perturbations, this is the second set, so both sets have the same thing, then you can show that you get a resonant peak in the gravitational waves, which is a characteristic prediction of such models. And this is the primordial spectrum perturbation and the black hole densities. That's how the gravitational waves, that's the black hole densities compared to the overall dark matter. You see for masses 10 to the minus 10 to the minus 6 m sun. For the set 1, we have these masses, and for the set 2, we have even smaller black hole masses, but they could constitute a significant fraction of the dark matter. The characteristic point of this model, of this hierarchy of scales, is this seesaw behavior in the profile of the gravitational waves, which exist on both sides. Here, the fraction of the black hole is only 0.1 of the dark matter. Here is 0.8. It's allowed by the parameters. In the second set of scales, you can have an enhancement due to an inflection point of the potential for some values of the parameter, but then you don't see this feature. So our model, which is characterized by an inflation driven by the string model independent action, will have characteristic features, although both models, this model in which the inflation is driven by the compactification action and prolonged by the B action, would lead to a smooth behavior, but our model will have intensely oscillating spectra, as we have seen here and here, and this may be seen in LISA. It could make falsifiable patterns in principle in future interferometers. Let me now come to the last part of cosmic evolution of the string GRBM. So far, I discussed a double inflation interpolated by Steve Materiva. This inflation was due to anomaly and it didn't involve fundamental inflatons. It was rather due to the non-linearities, h to the fourth term, fourth power of Hubble parameters of the energy density, like Starobinsky, but not quite. Now, chiral matter can be generated at the end of this RBM inflation from the decay of the vacuum, and the chiral matter, as I said, can cancel the primordial anomalies as required by naive different homomorphism invariants. So standard cosmology is obtained at the exit of inflation. But chiral anomalies can remain. U1 gauge anomalies or QCD anomalies can remain, and that could play an important role. So the whole cosmological evolution, which I will not is here, I will not describe in detail all this, but I mentioned them, is characterized mainly by the existence of some RVM inflationary de Sitter space, which is characterized by a constant undiluted Calvamon axial background, B0, the B dot is approximately constant, and that in theories that involve right-handed neutrinos, sterile neutrinos, which are generated at the end of the RVM inflation, the decays of these neutrinos in the presence of this background, which remains undiluted, but depends at the exit of inflation from the temperature, it leads to three-level symmetry violation in contrast to conventional CPT invariant that require a loop and three species of sterile neutrinos in order, at least two, in order to get CP violation. Here, with one species is enough, one flavor is enough. And this is the two widths of the decay of the sterile neutrino to lepton and antilepton, and they are proportional to this background. Some numbers, you may have a very heavy sterile neutrino, which can generate through schizo mechanisms the light sterile neutrinos, but you could have a hierarchy, and you could even have a KV sterile neutrinos. I will now come for, and only the two of them could be heavy. This could produce leptogenesis, and then through equilibrated electroweak baryon plus lepton number violating processes to involve these phalerons, you can communicate this leptogenesis to the baryon number. So that's the mechanism. The important role of the heavy sterile neutrinos is highlighted here. Chiral anomalies, of course, I discussed exist. So this B action can acquire masses through instanton. These are not words of instantons, but QCD instanton, and it could even acquire a mass in the order of the QCD action. And that, because the B action is related to torsion, that gives the promised geometrical origin of the action. So now we come to the modern era. The modern era, it still needs understanding. You can still phenomenologically parameterize it with the same epsilon, which needs to be understood here. But and you can see that if the today's Hubble parameter is 10 to the minus 33 V, that this value is the background has this form. In our microscopic model, you can estimate even the temperature. If there are no chiral anomalies, this B field scales like T to the cube, otherwise scales like T squared. Never mind, I won't bother you with details on this. We need to understand this modern era better, but the only point I want to say is that from the point of view of the alleviation of cosmological constants, that's the modern era today of the energy density. This comes from ordinary electromagnetic fields. This is positive in this particular case. And the h to the fourth term are not dominant today. This is the dominant today. And this has to be of order 10 to the minus 3 in order to fit the data. But this could alleviate both tensions, the H0 and the sigma 8. And how? Because you have a type 2b. From integrating out graviton fluctuations in our model, you get actually logarithmic times on not only integer powers, but also logarithm, and this play a role in alleviating this tension. That's one part. This I didn't want to discuss further. I want now to come to the role of axions and sterile neutrinos in dark matter in galaxies, and actually sterile neutrinos in the galactic structure. As I said before, the point of view I'm taking is that dark matter may consist of more than one dominant species, which depend on the era. Self-interacting dark matter plays an important role today in understanding dark matter simulations. And this, yes, thank you. That's enough for the time. And what we know is that, of course, large-scale structures, the self-interactions will not be visible, but they will make the individual galaxies more cold and spherical in depending on the cross-section. That's the lowest value, which can be obtained by various constraints, and that's the all constraints. And compared to the standard particle physics, this is 1 bound per GeV. but typical WIMP in dark matter in particle physics is 22 orders of magnitude below that. However, in modern observables using the dark matter drag and observing merging galaxies has given a more robust upper bound of this cross-section, 1/2. There are various observable, if you have a dark matter, there may be a mediating vector particle. Short-range interactions are excluded because they will lead to substructure evaluation, but long-range forces are allowed. And this is the model with as well as Ruffinian weather that we propose, that you may have a right-handed sterile neutrino dark matter of masses of order 50 keV with interactions in the dark sector stronger than the weak observable sector 10, so 8 orders of magnitude stronger than the weak interactions in the observable sector, and a massive exchange keV, which could lead to a core galaxy structure, which is more or less correct. That was the original profile. Of course, an important assumption is that we don't use the Einasto or Navarro French or white profiles, but we use the Ruffini, Arguelles, and Rueda profile, which is based on earlier works by Ruffini, who assumed that there is a Pauli exclusion principle gas of fermions, a Pauli exclusion principle obeying gas of fermions in the core of galaxies. Ruffini originally was assuming that maybe this gas prevents collapse. It doesn't collapse, and therefore there are no black holes in the center of galaxies. That assumption may not be true, since black holes have been photographed. However, what I'm going to present now on the masses are still okay. That is their profile without the Ceph interactions. Now, when you take the Ceph interactions, the core region needs to be revisited and is affected. And this is what I said earlier. I'm going to affect in our stringy model before I talked about the sterile neutrino of 10 to the 5 GeV, but there may be a hierarchy, and there might be more than one, and you might have a light one of 50 keV, which could play this role here. And these are some recent works that these constraints on warm sterile dark matter masses have been revisited. Now, what is the Ceph interaction? And I'm finishing. This is the model. That's the portal. We assume a vector interaction among either due to a contact term or due to a dark photon, which when you integrate out gives rise to these terms. And the measure of this, if the coupling of the field strength with a vector dark photon is GV, then this plays an important role. This coupling is important. You can assume that in the core of the galaxies, this coupling is there, and otherwise statistically is not significant. And you can get that the solutions of the Einstein's equation of motion for these fermions augmented with the thermodynamic conditions of Klein, there is no solution if the mass of the fermions is less than 47 keV or bigger than 350 keV, of course, which comes from collapse. Then the fermionic matter will gravitationally collapse to a black hole. So that's the allowed regime in this mass. Now, is it consistent? This, of course, that's the originally a RAR profile without halo profile without a Ceph interaction, and these are the profiles with Ceph interaction. You see, it makes the core more compact, or the 10 keV for instance. Now, and that's the Ceph interaction in order to have a cross section in the regime less than 1. You can find this sort of upper bound. Now, because of this portal, however, you have an important constraint. The heavy neutrino will decay to a Higgs and a neutrino, and then the Higgs will give rise to photons. These X-ray observations in the standard new MSM, non-interacting with the sterile neutrino of the keV, you can see that Perez and others, you can see that you can constrain around, there are some allowed regions in the 30 keV, 20 keV. These values have been updated recently by Carlos and his group, and it appeared also in a common MG16 talk. And you see that they use here self-interacting vector, our vector interaction, which affect the production, because you have a vector decaying to two self-interacting neutrinos, and therefore it affects the production, which the new MSM doesn't have. But the important point of us, and that's my final transparency, is that in general, the self-interactions or in general interaction with other dark matter species of actions will affect the profile and allow for masses higher than 40 keV. And these are actually the dark matter production through dark vector decays, for instance, is affected here. And these are in this regime, the allowed regime. Now, in this model, the actions and interactions with axial matter is through derivative couplings, but you may have even a non-derivative coupling through this compactification action, and these are the sterile neutrinos, and this can affect the situation, can even generate masses. I will not discuss here the situation, but I want to say that if in addition to the vector interactions with the sterile neutrinos, you assume this axion sterile neutrinos non-derivative interactions, you may have interesting effects in the course of galaxies, taking into account also that some of the actions can have masses of order of 2CD. Maybe both play a role in the galactic structure, and as we have seen also in these models, primordial black holes play a role. So let me summarize by showing again this cosmic cycle, which we make use of actions, torsion, and right-handed neutrinos. The stringy vacuum model is at the core of this, and the role of interaction of stringy actions and sterile neutrinos in the galaxies could play a role together with primordial black holes. And as an outlook, I finish now. Thank you very much. I leave this transparency as an outlook. We can look for this violation, for instance, using either CMB or GMB, the Lorentz violation, or this negative coefficient and all the action cosmology. Thank you very much.
Thank you very much. Okay, we are going to have now, if there are no...
Is there a question? It was very informative, so it should be a couple of questions.
Hello. Yes, I would like to make a short question.
Okay.
Hi, Carlos.
Nick, hello. Nice to see you again. Very nice, very impressive, ambitious program where you start from stringy motivated theories and can go through all the chronology of the universe from inflation to galaxies. Very interesting. So, I would like to know, do you think it is possible to have from this motivated theory you have put with distortion that you create this with this condensate, you create the actions, have both relics, actions, and external neutrinos that could play a role in the self-gravitating system of dark matter and galaxies?
Indeed, indeed. As I said, indeed, you will have the, for instance, you could have these two interactions. So you could have both a scalar, a pseudo-scalar,
so
interacting with the neutrino and the vector.
But sorry, this N and M bar.
Our sterile neutrinos. This is the sterile neutrino.
This is kind of this condensate forms an effective action. No.
Yes, these appear in the effective action. These interactions appear in the effective action. This is the condensate. The action could be a condensate, could even be linearly depending on time. But in principle, an excitation, this could lead to an additional source for production from the decay of this action if it is massive, you see? Like our vector was producing in our paper, it could have the same thing, it could be an additional source.
But if it's decay, then how it survives?
No, it decays the excitation of the action. There are many actions. There is always one action which survives because it may be very light. There are always very light, ultralight actions from compactification that can survive, that they cannot decay.
And okay, and last question is which physics out of this interaction may alleviate which sector in the cosmology? Do you think
this sector, of course, would affect the dark matter as we know in the galaxies.
Yes.
This sector with the actions could lead, as I said, to matter and antimatter asymmetry.
Mm,
So baryogenesis through leptogenesis.
mm.
And production of this sterile neutrino matter, for instance.
Okay, and final comment, I think if this may, one important test for this beyond standard model physics to test in cosmology is to see the effect in the linear power spectrum.
Absolutely.
As you know, we are starting this project of calculating the
Yes.
linear power spectrum out of self-interaction from Boltzmann equation.
Absolutely. That is
gravity.
actually the framework where you can see this.
Therefore, I think we could check this, Nick, if this your new interaction term can be put in our framework of this self-interacting.
It's a linear, it's a cubic term, action, and the coefficient is free because it depends on many models. There are many actions, so it's not restricted. You leave it free, and then it could be massive, massless. It could be stable. Indeed, it could lead to an interesting.
Yes, because this is some analogous to the ETOS program of
Absolutely, absolutely.
And could be interesting which effects can deal to the morphology of galaxies.
Yeah, I would be very much interested in this. I mean, as you know, I am interested in discussing.
Good. Then let's keep in touch with this.
Sure.
I think I'm interested to discuss these points. Yes, thank you, Nick. Thanks a lot.
Okay, we have another question by Jorge, please.
Hi, Nick. Hi, Nick. Good to see you again.
Hi, Jorge. Good to see you.
Look, about the interaction between the neutrinos and the sterile neutrinos. And you think that, for example, the neutrinos from a supernova explosion could get affected in their travel to the Earth by the interaction with the sterile neutrinos? I mean, for example, in the flavor oscillations or any other feature?
That is a good question, in the sense that, of course, for me, it's only, any coupling of action to sterile neutrinos would lead, in principle, to effects, depending on the coupling constant. It would also be a coupling of reactions to the photons as well, of course, to the FF dual term. So that would lead to Primakov processes. So if you have oscillations between the sterile neutrinos, that would back react to the actions. Absolutely. Absolutely. So it depends on how many flavors of sterile neutrinos you would have.
I mean, the neutrinos, sterile neutrino, I mean, ordinary neutrinos with the sterile neutrinos.
Ordinary neutrinos, I don't have this coupling because this would, I don't have this non-derivative coupling because it would break the SU2 symmetry. So it only happens to the sterile neutrinos. Because an ordinary neutrino is SU2. So the sterile neutrino is singlet under the SU2, so under the standard model group. That's why I cannot have this in with the standard model, unfortunately. Otherwise, it would be much stronger and it would be easier to see. I agree.
Yes, thank you.
Because you want to preserve the SU2 cross U1.
Okay. If there is no more questions, let's thank Professor Mavromatis again.
Thank you very much. My pleasure.
And we have a break now.
Yes.
I see that they are online via PETROSIAN and Bing Zhang. We will reconvene at 5 o'clock.
Yes.
And continue. And I'm very happy to see that Vahe is here. Thanks. And
okay, we have a break until 5 o'clock. So effectively, we have 22 minutes. See you.
Thank you.
Shortly.
Thank you very much.
Thank you. Yes, we have, it's time to start. So we have now Professor Vahe PETROSIAN with us. And I see your slides and see your mouse, so you can go ahead, please.
Shall I start then?
Yes.
Hi, everybody. I don't know how many people are still in the audience, but I'm not going to keep you away from your dinner. I know pretty close to your dinner time, so I'm not going to keep you away from it for too long, I hope. I'm sorry, because of time, I haven't been able to participate in this meeting, so I have really not very good idea what has been going on, what topics were discussed. So
this morning we had a splendid presentation of Maria Dainotti.
Good, yeah, good. I saw that.
We can send you the tape.
Yeah. Unfortunately, well, I'm familiar with Maria's work. I know what she presented, so I'm the co-author of the paper. Anyway, so I hope I'm not repeating things, but so this work I'm going to talk about is a collaboration with Maria Dainotti, who was at Stanford for a few years. And then some of the work is done by one of my undergraduates, Ili Kitanidis. And of course, our advisor on the statistics, our work involves a lot of statistics. Our advisor, Brad Efron of Stanford University Statistics Department, is a well-known statistician. He is the father of what we call the bootstrap method. Anyway, so let me show you the outline and get on. Well, I'm going to spend a few minutes, make some general remark about how we use GRBs as a cosmological tools, and then I will be clear from that we really need to find out the luminosity function and its evolution, the distribution in luminosity and redshift of the sources. And then I'll spend some time describing procedures which we have developed with Brad Efron on dealing with this sort of problem, and then result on the, I will present result on the long GRBs, more recent result from last year with Maria Dainotti on short GRBs. I don't think I will have time to have fast radio, but are very similar to GRBs, and we have done similar analysis. But maybe in some other occasion I can talk about that. Okay, there's been two possibilities of using gamma ray burst in cosmology. The most exciting part, or one exciting part, is that using GRBs as a standard candles to extend the Hubble diagram from low redshift obtained from supernovae remnant to high redshift available from GRBs. There's been many attempts to this, but unfortunately, in my view, they have not produced promising results, mainly because we have insufficient data to calibrate the data GRBs in a way one does Cepheid variables and supernovae remnant. But the second method GRBs can be used in cosmology is to use them as a probe of early universe. And this is what I'll be talking about. And this requires the thorough, detailed description of the luminosity function and its cosmological evolution. But of course, here we have dealing with luminosities, we have to assume a cosmological model. We are not determining cosmological model. So I will be talking about the second aspect for the rest of the time. If there's time, I may make comments about the first aspect, why it's not working so far. So the luminosity function and its evolution. We are dealing with determination of what we call a bivariate distribution of sources in luminosity and in redshift. And without any loss of generality, this distribution can be written as the form I've given below here, as a one depending on luminosity, combined luminosity and redshift, and then another one just redshift. This is the rho of Z here is what we call the co-moving density rate evolution, and G of Z determined here is the luminosity evolution. So this is sort of one approach where we assume that the luminosity distribution depends on redshift. And the alternative method is to assume that density, evolution depends on luminosity. This is called luminosity-dependent density evolution, which is also very common in dealing with extragalactic sources like AGNs. But I will use these are alternative methods, but I will use the first method because that's what our procedure produces. So the basic idea is we want to define this bivariate distribution in this luminosity redshift diagram. And given the fluxes and major redshift, we can produce such a diagram for all the extragalactic radio sources. This is a sample of 200 Swift gamma ray bursts shown there. But the problem of determining the distribution is because we are missing the sources in this red area, and we have to correct for this data truncation or this thing which the bias which is called the Malquis bias or Eddington bias. Long time ago, this were discussed in galactic sources. So there are two procedures to do this task. One is forward fitting method, and the other one is non-parametric method, which I'll call EPL. It's based on the work by Efron and myself, and which is related to very earlier work done by Lindenberg. In the forward fitting method, you have to, in addition to assuming cosmological model, you have to assume a form for the luminosity function. This bivariate distribution, you have to find out about if there's a luminosity evolution, what is the form of that, and the density evolution, what is the form for that all. And then you also, because to getting luminosities, you need spectral information. You need to have spectra fitting to. Anyway, all these several functions involve several parameters, 3 or 4 parameters. So in the, this procedure, forward fitting procedure involves minimizing something like a chi-square or maximum likelihood of fitting the data to the model in this multidimensional space, which raises question about its uniqueness. But so as a result, we have developed this non-parametric methods, which were done previously too. One of the first non-parametric methods for extragalactic sources was developed by Martin Schmidt for the study of quasars. Soon after discovery of the quasars, he used this V over V max method. It's a simple method that determines whether there's a density evolution. If there's the distribution of sources is uniform, then the average value of this V over V max has to be values of volume should be distributed uniformly with 0 and 1, so the average is 1/2. And Martin Schmidt used that to show that the quasars are evolving very rapidly. Was using only one moment of this distribution. Lindenberg generalized it, developed the C- method, which uses more distribution rather than just single moment. And I will come back describing that later on. But the problem with this very good non-parametric method is that they assume that the luminosity, the two variables, luminosity and redshift, are independent variables, or they're not correlated. So if that's the case, then this procedure can be used very usefully. But so the first thing one has to do is to test whether the two variables are independent. And this is what with Brad Efron and I, the method we produced is essentially to do that. So for the first thing one has to do find out whether the luminosity and redshift or the two variables are independent. And once you find out what sort of dependence they have, you can correct for that and define a new kind of luminosity, which is the evolved version of it, and therefore is independent of redshift. And then you can use those other methods I just described to define monovariate distribution in luminosity and redshift. So between luminosity function and density evolution. So that's the procedure. The best way to do a test of independence or the measure of correlation is to use this Spearman rank ordering test, where you look at the distribution of the ranks of the of each source among the population. And then there's this Kendall-Taw statistics defined by this equation where the R of j is rank of each source in the sample, and EIJ is expected the ranking, average rank, and VJ is the variance. So this Kendall-Taw statistic, if it turns out this value of tau is 0, that means the two are independent. If it's 1, means there's a 1 sigma evidence that they are not. If there's 2, there's 2 sigma, and so on. So this simple version of this has been used a lot. When you have untruncated data, you can do this very simply. Just find the rank of the sources among the subpopulation and determine this tau statistic. But unfortunately, we don't have untruncated data, and our method, the Efron-Petrosian method, is to account to do this ranking in a biased or truncated data. And let me spend a few minutes describing the essence of the method. Now, for each source, this is some luminosity versus redshift. This actually turns out not to be GRBs, but some quasar data, but the idea is the same. For each source shown by this red dot in the middle, with the luminosity L and the redshift Z, we can find out two other quantities: the minimum luminosity that the source like that should have to be included in a sample which is truncated by this lower flux threshold of the system of the sample. And the other thing is the maximum redshift that this source can have and be still included in the redshift. So we propose that instead of finding the ranking of each individual source in the population as a whole, which is truncated, you find its ranking among this, what we call the associated set of each source. Each source has two associated sets. If we're ranking in luminosity, for example, we will go to this box, square box, sources in this square box, n sub I, and those will be associated set sources, and we'll find the ranking in that sample, which, as you can see, is not truncated, it's complete. Well-defined luminosity limit and well-defined redshift limit. Or if you're ranking in the redshift luminosities, then you can use the blue box associated set in the blue boxes. So these are identical alternative methods of using this. So this is the gist of the procedure to find out whether there is a luminosity evolution or not. And this is an example of showing that tau statistic versus this parameter k. This we describe the evolution, luminosity evolution, by this function, which has actually single parameter k. There's another parameter z of c, which we introduced because evolution like this going to high redshift will be very fast evolution on high redshift, and there is not enough time in the universe for such a fast evolution. So we have to slow down the evolution at higher redshift, and this term on the bottom take care of that. Anyway, so as you can see, this gives a luminosity evolution factor K equal 3.4 with a 1 sigma relation very small. And this is very strong evidence for luminosity evolution, because the zero value of K is way up at many sigma. So we are many sigma away from independence. Okay, and once we have this function G of Z, as I said, we can go define the new luminosity, the evolved luminosity for the sources, and then we have separable monovariate distribution, and we can determine this simply. What the method actually does doesn't give you this differential distribution, but gives the cumulative distribution. And the idea is, once you have independence, it's very simple. It's demonstrated by this diagram, where suppose if you have you go two boxes here, N1, and there are two luminosities, high and low, and at low redshift, we see all the sources in these two boxes, so we know the ratio of N1 to N2. Now, if you go to higher redshift, if redshift and luminosity are independent variables, then we have to assume that this number of sources in this box N3 and this box unknown is same ratio as the ones in N1 and N2. And so this unknown number of sources X can be calculated this way. Of course, we don't do it by this sort of bidding and boxes, but for each source, we determine individually its contribution to the distribution. And this is how we can obtain the cumulative luminosity function phi integral of psi of L. It's just a product of sum of number of sources in the associated sets, or you can do the other variable redshift. In this case, cumulative redshift distribution is weighted by the volume of the universe, and then that depends on the other variable in the associated set MJ. And this way we can get cumulative and then take a differential of that to obtain the differential distribution. So this is the gist of this is the quick review of the procedure. Let me talk about some application. The first application I'm talking about is long GRBs. Most of the stuff I'll show is based on the 2015 paper by it was a senior thesis of Eli Kitinadis, and was done with collaboration with Korsavsky. And let me quickly go through the results. There's some problem with determining the complete function, well-defined truncation for gamma ray burst, because many observational thresholds come in selecting a sample. First of all, gamma ray, triggering in gamma rays, you have to have flux over some peak count flux threshold. So this is well known with most gamma ray detectors. And then you have to localize him, and Swift has done by the X-ray. And this introduces additional selection effect and additional threshold. And finally, you have to have the follow-up optical or use the UV out instrumental Swift to measure a redshift. So that in that case, the optical magnitude also comes in. So it's complicated. Well, there is some correlation between the X-ray and gamma ray distributions, as shown in this diagram. And then this correlation is very similar, or at least its distribution is very similar for the sources with redshift and without redshift. With redshift is the filled black dots in here, and without redshift is the open red circle. And you can see the distribution is pretty similar. But in any case, what in our methods, when we do this, we also use the X-ray threshold provided at this for the sweep sources in this article. So the method is become more complicated now, because now we have three-dimensional distribution: luminosity, gamma rays, X-rays, and redshift. So it's a trivariate distribution. But as I said, our method is pretty general, and we can be used in this case too. And I will show some results comparing the two ways of doing it. The optical is a little bit more complicated, but it turns out the optical and X-rays are more strongly correlated. And this correlation, it looks very similar for both those with redshift and without redshift, again, as shown by this distribution here. So X-rays could be a good proxy for optical selection effects too. So we are going to assume that, and I think that's a fair assumption. One would like to have more complete sample, but that's, we are right now with Maria Dei Noti, we are trying to use machine learning to estimate the redshift of this, the ones which are unknown, and that could solve this problem of uncertainty of what is the actual optical threshold. Anyway, so here is first result I want to show. Again, we're going to this luminosity redshift diagram, and you can see the points and the nominal flux threshold in gamma rays will give you this line. So the sample would be complete above this line. And if you take that raw data and find the correlation between luminosity and redshift, you get very strong correlation. Luminosity going as this 1 plus z to the 3.3 power. But of course, this is all because most of it is because the data is truncated, that it's a false correlation that is induced. So when we do our method, we find using that form of the luminosity evolution, we find the red line, which is weaker evolution. And then, of course, it has to be weakened at high redshift, because we don't have enough time in the universe to have a high luminosity evolution. Okay, so we didn't use this nominal threshold just to be conservative. We used the much higher, factor of 10 higher. This reduces the number, but at least we are sure that we have a complete sample. So once we have this evolution, then we can correct, and as I said, we can get cumulative distribution. And this on the left panel, I showed the cumulative luminosity evolution. The lower curve, it shows what the raw data says. If you just naively take the data, ignoring the selection biases. And when we use our method to correct, we get this higher curve, which means a lot of the weaker sources we are missing. Now we know what their distribution are. And usually this is looks like a broken power law with one index up here, and then you can fit it to a simple broken power law relationship, or a power law with an exponential cutoff. They provide as good as, and then once you have this fixed, you can take a derivative of it and obtain differential luminosity distribution. And the same thing in the redshift. This is the raw distribution of the number of sources with less redshift less than z, cumulatively going up. And now when we correct for the truncation effect, we get this black dots up here. And we also have calculated this sigma for ignoring luminosity evolution in case just turns out the luminosity evolution is not the correct thing for gamma ray burst. Again, we can fit this to some sort of analytic function and to get this derivative to obtain density evolution. And that we just concentrated on the density evolution. And this is what we get. This is a little bit of a crowded figure here. Again, we are showing the density evolution versus redshift, this capital Z, which is 1 plus Z. And the raw distribution is shown by this red dotted line. But when we correct it, just including only the gamma ray threshold, we get this black line. If we include both gamma ray threshold and X-ray threshold, which is sort of good proxy also for optical, we get this other distribution. And as I said, if we ignore the luminosity evolution, because there's no luminosity evolution, we have to have stronger density evolution, we get this higher curve. But now all these curves now are compared with the latest, one of the best estimate of star formation rate by Maddow Dickinson in their review article. And there's a slight newer version of this now, but not very different. And these are somewhat different than the earlier star formation rate people are used, especially at the low redshift. Star formation rates seem to be steeper now than they used to be. Anyway, so the main difficult difference, of course, is this low redshift. We get lots more gamma ray burst, rate of formation of gamma ray burst than rate of formation of stars. So that's a problem that we pointed out, and we're still looking at what is the answer of that. In fact, other people have done the same analysis using our methods, the same method, not forward fitting method, but our method. Here are the 4 other groups have done this, and all of them show strong luminosity evolution that we have found, that so confirm that. And this Yu et al. Paper shown by this cayenne color is using the same data as we did. This Conus wind is obtained from the gamma ray burst sample observed by Conus wind instrument, and that also shows excess at high redshift. Pascali et al. Did the same thing with the swifting, but with a much smaller sample because they tried to make it much more robust selection effect, a more complete sample. They get less, and in fact, they claim that there is no difference because they were initially comparing with the earlier star formation rate, which sort of, as I said, was a bit flatter at lower redshift. But even when you compare their result with the more recent star formation rate, there's significant difference. So I think all these things indicate that there is some discrepancy between rate of gamma ray burst formation and star formation. So this is a problem that we really need to address. Okay, now, so this is the summary of long GRBs. The short long GRBs can be used as a good cosmological tool for studying the early evolution universe. And I've emphasized the importance or the usefulness of non-parametric approach, which produces distribution with sort of minimal assumptions about anything. And we obtained the gamma ray rate evolution, which is somewhat different than a star formation rate. So we have to, as I said, to further study, obtain bigger sample, and maybe one of these days we'll be able to use them as standard candles and determine the cosmological parameters at high redshift, extend the Hubble diagram at high redshift. That'll be pretty exciting. Okay, let me now talk about spend. I don't know how much time I have, maybe another 5 minutes. Talk about short gamma ray burst. This is a more recent paper by Maria De Noti, myself, and an undergraduate student at Bowdoin. And do exactly the same thing for a short gamma ray burst as we did for long gamma rays, except problem is more complicated here because we have much smaller number of short gamma ray bursts. And so we cannot do all the tests that I presented for long gamma ray bursts to make sure we have a complete sample. So we had to have a different approach to make sure that we have a sample which is not biased or has a minimum bias of flux threshold only. So in this slide, I'm showing on the top left the distribution of the fluxes in green of all the short gamma ray bursts we collected from Swift at the time of the publication of the paper. And the black histogram shows those with redshift. A good fraction of the sources have redshift. Now, the main question is, are these two population, are the ones with redshift we can use for our analysis, this drawn from the same population as the complete sample shown by the green histogram. So we do one simple test for this. We do is a chromograph Smirnov test, where you compare the cumulative distribution of fluxes up to some assumed threshold. And this lower left diagram, I show such a test for assuming that we have the sources are cut off at this flux shown by the blue line. And then we compare the cumulative distribution of the sources with redshift and all of them. And as you can see, this distribution, normalized distribution, very similar, indicating that probability that these two are drawn from the same sample is very high. And in fact, if you can see for all the fluxes above this threshold of 6.34, shown here, the p-value is very close to 1. So it's highly probable that those with redshift at these fluxes are drawn from the parent population, which included all the sources. In fact, so in our analysis, we used that as the flux limit. And that is shown by in the lower right diagram of luminosity versus redshift by this dashed line as the cutoff threshold for the luminosity. We also used this other cutoff just as a test, where again the p-value is pretty high, and we have that is shown by this solid black line in here as the threshold. And so now we have two samples, two subsamples, which could be both complete. And then we carried the analysis for both of them. And first of all, we find the luminosity evolution as before. And in fact, actually here we tried 3 samples, the other one too with even higher luminosity. And you can see that luminosity evolution, the 0 of this tau statistics and the value of k around 5 or so is very similar to all 3. But here the evidence is not as strong for luminosity evolution because the 0 tau is indicates there's only 2 or 3 sigma evidence that there is luminosity evolution. Okay, so correcting for this luminosity evolution, now we can calculate the cumulative distribution. Again, it's very similar to what I did for long gamma ray bursts. I would go with the top. These top 2 are the cumulative distribution for the more complete sample. and this is at the lower flux level. And you can see they're very, very similar. Again, you get the raw and then cumulative distribution, except now we have a little bit different luminosity function that we get in long gamma ray burst as this high rise at very low luminosities in short gamma ray burst, which is not present in a long gamma ray burst. And the cumulative density distribution, again, with and without luminosity compared with the raw. And then we get the differential luminosity function, the derivative of this, and the derivative of this gives you the density evolution. Again, the two dot and the solid lines are for the two samples. The raw corrected with luminosity evolution and without luminosity evolution. So all this test. Again, show this essentially continuous decline, and again, very high number of the redshift. The next slide shows this thing a little bit better, eliminating some of the problem. So the red line is our sort of best estimate of the density evolution of short gamma ray burst, and shown on the left. And on the right is the paper from Paul, because we expect short gamma ray bursts to be from a merger of neutron stars and neutron stars and black holes. Their rate of formation has to be delayed relative to star formation rate. Paul, for example, assuming this star formation rate, he used different kind of distribution of delayed. And I think Tsvi PIRAN and Vanderman also did a similar calculation. And they find out that this is the type of formation rate you expect for delayed things, which would be appropriate for gamma ray burst, short gamma ray burst. And that sort of roughly agrees with this curve. So at least in the case of short gamma ray burst, we don't have this big difference between star formation rate and expected short gamma ray burst. But there is still maybe more at low redshift, but not very significant. So my one last thing I want to comment is how do this short and long gamma ray bursts compare with each other? We have done some analysis of this as well. This diagram showed the redshift distribution of swift long gamma ray burst in black, and in sort of this yellow-green is the short gamma ray burst redshift distribution. And we have compared all the properties, a lot of the properties of this short and long gamma ray burst at the low redshift, at redshift below 1, where we see different deviation from star formation rate, and long gamma, high redshift where we don't see it. And we find some differences between this behavior. So there seems to be some similarity between the low redshift long gamma ray burst and short gamma ray burst. So it's possible that those low redshift short long gamma ray bursts also are merger events rather than collapsar, that we think that's why they don't follow star formation rate. Now it's a lot more work. Maybe there are machine learning estimate of redshift can resolve this. That'll be the best way to do it. But if that's true, this will be, this is a summary of what I found short gamma ray burst, but also this is very important consequence for rate of gravitational wave production. So I think I better stop here now. I think I've run pretty close to my 35 minutes or so. And I was going to talk about using the gamma reverse as standard candle. If a question comes up, I can address that too. So I will stop here and see if there are any questions.
Okay, let's thank Professor PETROSIAN for this nice talk. And if someone has questions or comments, please. Okay, Soroush, you can unmute yourself.
Can you hear me, Vahe?
Yeah.
Yes.
Thank you for very interesting talks and nice to see you. My question is related to the point that you mentioned about this redshift dependence of the luminosity.
Yes.
If you know, some groups considering these GRBs in the rest frame of the source means they use some correction which comes from this luminosity distance, you know, assuming you have this isotropic emission of the sources. This you know, could you comment on this and if these two methods are somehow related?
Yes, I think I didn't emphasize, you are correct, that all this work, we are assuming we're using luminosity, which is assumed it is isotropic. There's no correction for the fact that they may be jetted and the luminosity may be in general, as far as the rate is concerned, this won't make very much difference because the rate still, if they're beamed, of course, their luminosity will be higher, but their number will be lower. There'll be fewer pointing to us. So it will be, at the end, the density evolution will not be affected as much. But the luminosity function, of course, it will. We'll have a different kind of luminosity function.
I see. My second question is coming back to the last point that you said about using this machine learning approach to predict the redshift of the sources. Did you, I mean, can you say about the parameters that you used in your approach somehow to predict, I mean, the duration T90, which parameter are you expecting in your, these machine learning methods to predict this redshift?
Okay. I was hoping that maybe, in fact, Maria De Noti earlier talked about this, but we use...
No, I haven't.
Maria, you want to address this?
Yes,
yes,
I'm happy. Yes, I'm happy to address. So we tried many parameters, and we found out that the parameters that best work for redshift estimation are T90, the flux at the end of the plateau emission, time at the end of the plateau emission, fluence, and the spectral index in the afterglow. So currently we are using a sample of 116 gamma ray bursts observed in optical. Initially, we started with X-ray, but eventually we realized that the optical emission is more promising for this analysis. And we tried many methods combined together through an ensemble method that it is called super learner. Yeah, today I didn't have time to explain all of it, but I mentioned briefly. Yes.
Okay, thank you so much.
Yeah. And any other questions?
Well, this is very interesting. We are trying to approach in a different way. Of course, this is the reason why we are so interested in your earlier work, to try to understand why a given source changed the T90 and what is the physical difference as a function of Z of the luminosity, looking at our understanding of GRBs. And of course, the relation between short and long in our model is very simple, because from the late evolution of long GRBs, you have the short one, and therefore we are very interested in your statistical analysis. But we will focus mainly how a luminosity of a source in the BDHN model changes with Z. We will present to you some data in the next 2 days, and then we will discuss with Vahe, and eventually, if Maria Giovanna will be present, now
Yes,
the
yes, I
time
will.
will be on 17 to 17:45 on Wednesday evening. I will send to both of you our consideration, to Giovanna and to Vahe.
Great, that'll be very nice. Thank you, Remo. And I'm
Thank
looking
you.
forward to hearing more about it and discussing it.
And it's really great. These meetings are working as very effective changes, and they work well. Although we cannot travel, I think to use the different timing allow us to keep contact and do real progress. I am really impressed by the success. We are making progress in the understanding with PIRAN, with Narek on such a new topic like cocoon and so forth. And we are very excited about this communication we are having. Thank you again. Say hello to everyone in Stanford. And if you find a moment, just say hello to our good Francis Everett. I think he will enjoy your visit.
Yeah, I will. Thank you.
Okay, all my best. Bye.
Bye-bye.
Okay, thank you again.
For sure.
Now we can close this session, which spans from Japan to US. It was very nice to hear you all, to ask the questions and take the answers. So thank you again, and see you tomorrow. Tomorrow we have the continuation of our school. Thank you.
Berlan, congratulations to your chairing. You did a quite good job.
It was a pleasure.
Now go
Thank you.
back to the salt mine, and let's work on the paper on the supernova without losing a single instant.
Okay, thank you. Thank you. Goodbye.